F-18 versus modern radar, how it stays undetected. Modern radar systems are incredibly advanced. They can monitor vast areas, track objects at long distances, and process enormous amounts of data in real time. So how does an aircraft like the F-18 Super Hornet continue to operate effectively in such a highly monitored environment? At first glance, it might seem like a contradiction. The F-18 is not a full stealth aircraft in the same category as newer fifth-generation designs. And yet, it remains one of the most widely used and trusted platforms in modern naval aviation. So what's the explanation? The answer is not a single feature or breakthrough. It's a carefully engineered combination of design, onboard systems, flight performance, and network integration. This is not a story about invisibility. It's a story about intelligent engineering and system-level optimization. Understanding modern radar systems. To understand how the F-18 operates effectively, we first need to understand what it is interacting with. Modern radar systems are no longer simple tracking tools. They are part of integrated networks that combine long-range detection, signal processing, and data sharing across multiple platforms. These systems can identify patterns, filter noise, and maintain awareness across large regions. However, even the most advanced radar systems rely on fundamental physical principles. They emit electromagnetic waves and analyze how those waves interact with objects. Detection depends on how much energy is reflected back. This means one critical factor defines visibility: signature. The larger and more reflective the signature, the easier it is to detect. And this is where aircraft design becomes essential. Signature reduction through design. The F-18 was not originally designed as a stealth aircraft. However, the Super Hornet variant incorporates multiple refinements that reduce its detectability. This approach is known as low observability through signature management. Instead of eliminating detection entirely, the goal is to reduce and control how the aircraft appears to sensors. This begins with geometry. The aircraft's surfaces are carefully shaped to redirect incoming radar waves, minimize direct reflections, and reduce strong return signals. Edges, panel alignments, and surface angles all play a role in managing how energy is scattered. Another important element is the engine intake design. The front of a jet engine is highly reflective to radar due to its rotating components. To address this, the F-18 uses curved intake ducts that limit direct visibility into the engine. This significantly reduces one of the strongest potential reflection points. In addition, selected areas of the aircraft are treated with radar-absorbent materials, or RAM. These materials help reduce the intensity of reflected signals by absorbing part of the energy. Rather than covering the entire aircraft, these materials are applied strategically to maximize efficiency while maintaining practicality. The result is not invisibility, but a controlled and reduced signature that supports more flexible operation. Electronic awareness and sensor systems. Physical design is only one part of the equation. Modern aircraft rely heavily on electronic systems to understand their environment. The F-18 is equipped with the AN/APG-79 AESA radar, a highly advanced system capable of rapid beam steering and multi-role operation. Unlike older mechanical radars, this system can scan different areas almost instantly, track multiple objects simultaneously, and operate in different modes without interruption. It also supports low probability of intercept, or LPI, operation. This means it can function in a way that is less noticeable to external monitoring systems. Alongside active sensing, the aircraft also uses passive detection systems. These systems monitor the surrounding electromagnetic environment without emitting signals. They can identify sources of activity, determine direction, and provide early awareness. All of this information is processed and combined into a unified interface. This concept is often referred to as sensor integration. Instead of presenting raw data from multiple sources, the system delivers a simplified and coherent picture. With the addition of systems like IRST, infrared search and track, the aircraft can also detect thermal signatures. This provides another layer of awareness without relying on active emissions. Flight performance and adaptability. Another key factor in how the F-18 operates effectively is its flight performance. The aircraft is designed for stability, control, and adaptability across a wide range of conditions. One of its defining characteristics is its ability to operate at high angles of attack. This allows the aircraft to maintain control even in extreme flight positions. From an operational perspective, this capability supports rapid directional adjustments, precise maneuvering, and flexible positioning in complex environments. The aircraft is powered by two General Electric F-414 engines, providing consistent thrust and system redundancy. This dual-engine configuration enhances reliability and allows continued operation under demanding conditions. In addition, the F-18 can operate at varying altitudes, including low-level flight. By adjusting altitude and position relative to the environment, the aircraft can manage how it appears to external systems. This is not about avoiding detection entirely, but about managing exposure and timing. Network integration and data sharing. One of the most significant advancements in modern aerospace systems is connectivity. The F-18, particularly in its Block 3 configuration, is designed to function as part of a broader network. Rather than operating independently, it exchanges information with other platforms in real time. This includes airborne early warning systems, other aircraft, and surface-based systems. Through high-speed data links, the aircraft can receive and share information across the network. This allows it to access external sensor data, build a more complete operational picture, and coordinate with other systems efficiently. The onboard processing system, including the Distributed Targeting Processor Network (DTPN), plays a central role in managing this information. The cockpit interface has also been modernized with large-format displays that improve clarity and usability. This networked approach transforms the aircraft from a standalone platform into part of a coordinated system. Continuous evolution. Another reason the F-18 remains relevant is its ability to evolve. The Block 3 upgrade represents a significant step forward in processing power, connectivity, and operational lifespan. The aircraft's service life has been extended to approximately 10,000 flight hours, ensuring long-term usability. New features such as conformal fuel tanks improve range without compromising aerodynamic efficiency. These updates allow the platform to remain effective in changing technological environments. Rather than being replaced, the aircraft is continuously refined. So, how does the F-18 operate in the presence of modern radar systems? Not by relying on a single advantage, but by combining multiple elements into a cohesive system. It uses optimized geometry to manage reflections, advanced materials to reduce signature, integrated sensors for awareness, strong flight performance for adaptability, and network connectivity for enhanced information. Each of these components contributes to a platform that is flexible, reliable, and effective. The F-18 demonstrates that performance is not defined by one feature alone. It is the result of integration, balance, and continuous improvement. What do you think about this approach to aircraft design? Is system integration more important than pure stealth? Share your thoughts in the comments. And for more deep dives into aerospace engineering, subscribe to Aerotech Insight.